Transforming a geological prospect into an energy asset that will produce for half a century requires a meticulously orchestrated 50 to 60-day battle against extreme subterranean physics. In the early days of extraction, engineers lacked the mechanics to control the pressure they uncovered. Success often meant a chaotic, uncontrolled eruption of oil directly into the sky. To bore deep into the Earth safely, modern crews must apply immense rotational force, or torque. Traditionally, they achieved this with a Kelly drive. A massive hexagonal steel pipe, called the Kelly, sits tightly on the rig floor and transfers rotation to the drill string below, advancing the hole 30 feet at a time. But the Kelly system has a major operational flaw. To attach the next 30-foot segment of drill pipe, operations must stop completely. The crew has to pull the drill bit off the bottom of the wellbore and temporarily halt the flow of protective drilling mud. Stopping that fluid circulation leaves the steel drill pipe highly vulnerable to getting stuck in settling rock debris. For deep, highly complex wellbores, those constant manual connections and frequent downtime risks were simply too expensive to maintain. The modern solution suspends the rotational power entirely above the rig floor. The top drive system uses a powerful motor hanging directly from the traveling block, grabbing the pipe and applying torque from the top down. This chart compares the high connection frequency of traditional 30-foot pipe sections with the top drive's capacity to drill using pre-connected 90-foot stands. By tripling the length of the drilling intervals, the top drive cuts connection downtime by a massive 66%. As this updated view of the data illustrates, that exact drop in connection frequency correlates directly to a severe drop in stuck pipe incidents. Because the top drive requires fewer mechanical stops, the bit stays on the bottom, allowing protective drilling fluids to circulate continuously. By moving the primary rotational mechanism off the rig floor and automating the pipe handling, the crew stays out of harm's way. Additionally, using standard round pipe instead of the hexagonal Kelly protects the rubber seals inside the well safety valves from tearing. Thousands of feet underground, all that automated surface horsepower arrives at a single focal point, the drill bit. Here, kinetic energy translates into the brute force required to degrade solid rock. For decades, the industry relied heavily on roller cone bits. These tools require immense weight on bit, thousands of pounds of thick-walled steel pipe pressing down from above, so their interlocking teeth can compressively crush rock formations with strengths exceeding 30,000 psi. But sedimentary rock has much lower shear strength than compressive strength. Polycrystalline diamond compact, or PDC bits, exploit this physics. Fused with incredibly hard synthetic diamond cutters, these stationary blades slice across the rock face, stripping it away through transverse shearing rather than heavy crushing. This visualization highlights the economic advantage of shearing. Replacing roller cones with PDC bits increased the drilled distance per bit from 800 to 2,400 meters. This efficiency shrank a 28-day schedule to 19 days, saving $4 million per well. Applying advanced material science to drill bits shifted the mechanics of rock destruction from heavy compression to high-efficiency shearing, permanently lowering the cost of deep extraction. As the bit shears through the earth, the well requires a closed-loop circulatory system to survive. High-pressure surface pumps push heavily engineered drilling mud down the hollow pipe to cool the bit and blast rock cuttings away from the cutting face. This mud provides a critical function called hydrostatic overbalance. Engineers precisely weight the fluid so that the downward pressure of the mud column is slightly stronger than the outward pressure of the surrounding rock. This holds the raw dirt walls open and stops volatile subterranean gases from rushing into the well. When that mud makes its return trip to the surface, it is loaded with destructive rock debris. This cascading flowchart tracks the strict mechanical filtration required to purify it. The fluid vibrates through a shale shaker to remove large chips, spins through a centrifugal desander, and finally passes through a desilter, filtering out microscopic silt particles down to 20 microns. If a crew were to skip this microscopic filtration process, the highly abrasive rock silt would remain in the mud, circulating back down the hole and rapidly destroying the multi-million-dollar surface pumps. Because drilling is effectively a blind operation, engineers use measurement while drilling, or MWD, to steer. Sensors packed right behind the drill bit read the exact 3D trajectory of the wellbore and send that data up to the surface using mud pulse telemetry, literally pulsing specific pressure waves into the flowing drilling mud. In offshore environments, before the bit touches the seabed, operators face the preliminary challenge of establishing a perfectly stable surface platform over the open ocean. In deep water, rigid steel legs can't reach the seafloor, so floating vessels must hold their exact coordinates. They generally rely on either standalone dynamic positioning, which uses active thrusters to continuously fight ocean currents, or thruster-assisted mooring, which physically anchors the vessel to the seabed. This comparative chart proves the life cycle efficiency of the moored approach. Thruster-assisted mooring drops continuous thruster use by 21.5%, lowering fuel burn and emissions. Despite heavy upfront logistics, it crosses the economic break-even line against the standalone system at 57 days. Whether it's interpreting pressure pulses to navigate invisible rock layers or deploying heavy anchors to lock a vessel in deep water, data-driven positioning turns a highly chaotic environment into a calculable, controlled space. As the drill bites deeper, the raw rock must be permanently supported. Engineers line the hole with telescopic steel casing and secure it using a Lucigen 2-plug primary cementing method. Heavy cement pushes a rubber wiper plug downward until it hits a float collar, bursting a thin rupture disc to allow the cement to flow outward and seal the gap between the steel and the earth. If the hydrostatic weight of the drilling mud ever fails to hold back the Earth's natural pressure, an event called a kick, the rig relies on the blowout preventer, or BOP stack. This towering assembly of hydraulic valves is bolted to the wellhead as the ultimate failsafe. When standard seals aren't enough, the BOP deploys its absolute last line of defense, the shear rams. Driven by extreme hydraulic force, two massive hardened steel blades slam horizontally together, completely severing the heavy steel drill pipe and crushing the ends flat to permanently trap the pressure. All the high-speed top drive automations, diamond cutter efficiencies, and offshore fuel savings mean absolutely nothing without these heavy mechanical failsafes guaranteeing environmental integrity. Even when a well is safely cased and cemented, the oil still can't flow into the pipe. To initiate production, engineers lower explosive perforating guns to the exact depth of the hydrocarbon reservoir. They detonate shaped charges, blasting high-velocity plasma jets through the steel and concrete to create physical tunnels into the rock. Initially, the reservoir's natural subterranean pressure is strong enough to push the oil and gas to the surface. But as that pressure inevitably depletes over decades of extraction, the upward push weakens. Engineers must install artificial lift systems to defeat the weight of gravity. For shallow wells with lower fluid volumes, they use familiar mechanical surface pump jacks. But for deep wells requiring massive liquid recovery, they deploy electric submersible pumps. These sit at the very bottom of the wellbore, utilizing high-speed centrifugal force to push tens of thousands of barrels upward. In wells prone to abrasive sand, engineers rely on fluid expansion, known as gas lift. High-pressure gas is injected down the casing and into the fluid column. This creates bubbles that artificially lighten the weight of the liquid, allowing the remaining natural reservoir pressure to easily push the mixture the rest of the way up. From the dynamic stabilization of surface rigs to the mechanical ingenuity of downhole pumps, an oil well is a meticulously engineered, data-driven machine. Every component is designed to safely harness and control extreme subterranean physics.